In today's video, I'm going to show you how to solve this problem. Let's look at the problem. Shortly after opening her parachute, a free-fall parachutist of mass 60 kilograms, including the equipment, experiences the forces shown in the diagram. In this problem, I'm going to show you how to find the magnitude and direction of her acceleration. Take acceleration due to gravity to be 9.8 meters per second squared. And this is the diagram. We have a parachutist that weighs 600 newtons. And also there is air resistance or air drag on this parachutist pointing upwards of 900 newtons. Let's look at the solution. Given the mass of the parachutist as m equals 60 kilograms. Also given the weight of this parachutist as 600 newtons. And also given the air resistance, that is the force of drag, as this parachutist is falling downwards, as F air equals 900 newtons. Take acceleration of free fall to be 9.8 meters per second squared. So this is the data we are given in this problem, and from this we can solve the problem to determine the acceleration with which this parachutist was falling downwards. The next thing is to choose a direction and also draw a free body diagram. So I'll choose the direction such that since this motion is vertically downward, I can choose a coordinate system with the vertical axis representing the motion in the vertical direction, and we do not have any horizontal motion. The x component of this motion will not be considered. And in this coordinate, we are choosing forces that point upwards to be positive and forces that point downwards to be negative. With the free body diagram, we can represent the parachutist as a point particle with the weight acting vertically downwards, and that is equal to mg. That is the mass of the parachutist times the acceleration due to gravity. So that is the gravitational pull on this parachutist. And then in reaction to the weight, since there is a parachute, there's air drag on this parachutist which points upwards. That air drag as F air equal to 900 newtons, with the weight also equal to 600 newtons. Like I mentioned, in the horizontal direction, we don't have any motion since this is a purely vertical motion. However, we are looking at it in terms of dynamics, that is referencing all the forces acting on this object. Okay, so to do this, we need to apply Newton's second law. And what does this law say? It says the net force, that is the sum of all forces acting on this parachutist. So sum of all the forces is equal to the mass of the parachutist times acceleration of the parachutist. That is Newton's second law, and we are going to use this law to solve for the magnitude and direction of the acceleration. From this equation, we can isolate the acceleration by simply dividing both sides of the equation by m. So if we have the net force, which is sum of all the forces, equals the mass times acceleration. Now we can divide both sides, that is the right hand side, by the mass, and the left hand side we have to do the same thing, we divide it by the mass. Okay, now we can see that the mass cancel out, and then we have the acceleration to be equal to the net force acting on this parachutist divided by the mass of the parachutist. Since we have this, we now have to sum all the forces acting on this parachutist in the vertical direction. To do this, the sum of all the forces, we can see that the forces acting are upwards is the air drag, which is F air, and then downward is negative per our coordinate system. So that is minus the weight, right? So we can substitute our values. So we will have 900 newtons minus 600 newtons, which is the weight. So the net force is going to be equal to 300 newtons. Okay, now what is the mass? We know the mass to be 60 kilograms. So we can plug that in our equation here. So the net force, which is 300 newtons divided by 60 kilograms. Now 60 into 300 will give us positive 5. And then the unit is going to be Newton per kilogram. However, we know the definition for a Newton is the force required to accelerate 1 kilogram of mass, an acceleration of 1 meter per second squared. So in that case, we can see that this Newton is nothing but kilograms times meters per second squared. So the kilogram will cancel the kilogram, and then we will be left with meters per second squared. So the acceleration is going to be 5 or positive 5 meters per second squared. So with this, we can rewrite it clearly. So we can have the acceleration to be, we found it to be A equals plus 5.0 meters per second squared. All right, so from this, we can tell that the magnitude of the acceleration is 5. So the magnitude is 5.0 meters per second squared. And then direction is what? Upwards. So positive means upwards. And what is the physical consequences of this? Even though the parachutist is accelerating downwards, but the net acceleration is upwards. So that means that this parachutist is rather slowing down. So this is the power of Newton's second law, because we need to account for air resistance in this case. Unlike in kinematics, when we look at motion without any references to the forces, we only describe the motion in terms of its position, velocity, and acceleration. We see that it undergoes just free fall without any forces, so we have to neglect air resistance. In dynamics, we need to account for air resistance, and we can see that as this parachutist is falling downwards, there's air resistance that slows them down, and that is the consequences of our result. And we have to define our coordinate system, meaning upwards, which is positive direction, means the net acceleration is upwards. But it doesn't mean the parachutist is rather moving upwards. It just means that as this parachutist is falling downwards, instead of speeding up, it slows down. So the parachutist will be slowing down until they hit the ground. All right, so this is the problem on Newton's second law. And if you enjoyed this, hit the like button, subscribe. Don't forget to share so that your friends and colleagues can also have access to this resource. Until then, I'll see you in the next video.